Yeah, so it's our pleasure to have George here to share about his work on a post-variational strategy for quantum machine learning. Um, so this time it will be our first physical seminar, so it's good to see you guys in person. But also, yeah, thanks for joining over Zoom as well, and hopefully you'll be able to see you in person sometime in the future. Um, so now I just you pass on to George to share about his work. And
Okay.
George, the floor is yours.
All right, thank you, Vinny. So my name is George. Can everyone in the Zoom hear me all right?
Yes.
Okay.
Yep.
All right, great. Okay, so today I'm going to talk about post-variational strategies for quantum machine learning. Okay. Oh, nice. All right. So in what current quantum computing looks like, there are two main models, I would say. So the first one is the variational quantum algorithm. So these are more near term. So generally, the idea is to have parameters on your quantum computer, and then you kind of tune it, do measurements on that computer, pass it over to a classical computer to update those parameters and send it back over to the quantum computer. Okay. So these are more like near-term solutions for a quantum computer. Okay. So however, some problems such as barren plateaus and the fact that there are few theoretical guarantees that exist in this type of this type of computing is a problem to how these near-term computers operate. Okay. So the more familiar part of quantum computing is what we call fault-tolerant algorithms. So these include your Shor's algorithm, Grover's algorithm, and HHL algorithm. So these algorithms rely heavily on fault tolerance, which is the absence of errors within the computing itself. So the problem with this is that with the current technology, there's not really any fault tolerance yet, or not a lot of fault tolerance. And the system size for hardware may scale quite largely because due to the fact that you need error correction to achieve these types of algorithms. Right. So with these two main models having some problems in or some hardness or some difficulty in implementation, the question we want to ask is there some other way of combining classical computers and quantum computers to have some type of hybrid quantum classical computation? Okay. So here I would like to talk about what we call post-variational strategies. So these are strategies that convert the problem from an optimization or computation problem over quantum circuits to a classical convex optimization problem. Okay. So basically what we do is to use quantum computers to compute values from fixed ansatz or guesses or quantum circuits or certain observables and use classical computers to find the optimal combination. Okay. So so from a computer science standpoint, if the variational algorithm looks like a neural network, this would look something like an ensemble strategy. Okay. So the idea is to just move the parameters. Oh, okay. So if we're taking a variational algorithm as a backbone for our design, what we do is basically we just take the parameters from the quantum model and we move it over to the classical model. Okay. So this is generally the idea of how we design our post-variational algorithm. So because it's based from the idea of the variational algorithm and we convert it over to a post-variational to our type of ensemble type algorithm, we call it like a post-variational algorithm. Okay. So for post-variational algorithms or post-variational strategies, I believe there are two types of these type of strategies. So the first one is what we call a problem-inspired approach. So what are these problem-inspired approaches is where you have a target Hamiltonian and you're trying to learn the ground state. So problems like these. Okay. So for these problems, we're supposed that we're given a linear decomposition of the target Hamiltonian in a series of unitaries. And so now we have information of the problem itself, which is the Hamiltonian. How do we use it? So basically, we use it to construct multiple ansatz with the decomposed components. So for each unitary, we try to build our ansatz based on these decomposed unitaries. And then from these ansatz that we construct, we find the optimal combination of these quantum states. Okay. So this is actually not like a new idea that we propose. It's actually been used in various applications already. So such as linear systems, quantum eigensolver, quantum simulation, as well as semi-definite programming. So these are all very good papers that use this type of idea as the backbone for optimization. Okay. So what we would like to talk about for the first part of my talk, what I'd like to talk about is based on what we call problem agnostic approaches. So these are problems where you don't have a target Hamiltonian or some fixed problem. So let's say these are problems that are more similar to, let's say, classical machine learning problems. So if we're given a data set and some labels, can we learn some sort of model that could predict predict a label based on these the given data? Okay, so this is more on like the supervised learning side of machine learning if we're talking about computer science. Okay, so for these cases, there's no baseline Hamiltonian to base your ansatz on. So how do we build them? Basically, the idea is to fall back to the variational principle. So we take a variational ansatz, and then we try to create multiple fixed ansatz based on that, and we find the optimal solution. Okay, so there are three ways to looking at this approach. So the first way is, well, these ideas are more there's inspired by the different pictures of quantum mechanics one can see, but they're not exactly the same as, well, time evolution stuff. But this is generally the inspiration. So the first inspiration is the Schrödinger picture. So this is where you fix the observable, and then you find the optimal combination of quantum states. So this is basically the ensemble version of the variational principle. Okay. So the other idea is when the Heisenberg picture would involve the observable. But in this case, what we do is we discard the ansatz altogether and construct the observable based on from basic blocks such as polys. Okay, so these would so we just measure the quantum state directly on these observables based on, such as polys, and then we find the optimal combination of these polys that build up to the Hamiltonian. Okay, so this is the second picture. The third picture is inspired from the interaction picture, which is basically just a combination of both. We have some ansatz, and we also build the construct the observable from polys. Okay, so I'll go into in depth about these later. Okay, so this is basically an overview of what we call post-variational strategies. Okay, so for now, I'm going to talk about the first work for today, which is post-variational quantum neural networks. This is a joint work by Patrick Urbankaus. Okay. All right. So for this paper, neural networks neural networks are used to learn some unknown model within classical computers, computer science. So basically, in this setting, what we want to deal with is problem agnostic approaches. Okay. So starting from the variational algorithm, which is familiar, we have some embedded quantum data. We transform these data by some parameterized quantum model to some quantum features, and then we do some measurements. So this is basically the outline of the variational algorithm. So how do we convert it to the post-variational algorithm? So there's two ways. The first way is to expand this ansatz over here into different combinations of other ansatz. And the second way is to measure on different types of observables. Okay, so the first idea is to expand this directly. It's called what we call the ansatz expansion strategy. So basically what we do is we take a variational ansatz here, which is parameterized by some theta. Okay. It's yours. Okay. Parameterized by some parameter theta. Okay, so what we do is we select a good initial point, theta 0, and then we just basically do Taylor expansion on this ansatz to generate different types. Okay. So how do we do this? Basically, in variational algorithms, we can take the gradient of some quantum circuit by what we call something called the parameter shift rule. So if we want to do Taylor expansion, the idea is to just fix an initial point, but instead of iteratively updating that parameter, we just expand directly and up to higher derivatives such as the Hessian or third order and so on and so on. However, a thing to be noted is that the number of measurements required is actually exponential to the derivative order to be taken. So basically, when you want to take a gradient, for a parameter shift rule, you need two other circuits to construct the gradient. Then so that grows, the number of circuits that you need grows exponentially to the derivative order that you take. So in order to restrict your the growth of your quantum circuits to some certain level, you have to truncate at some smaller degree. So a low order truncation is needed, but the problem is it might not be effective for some estimation. Okay. So bringing it back to what I mentioned before in this strategy, the important point is that you start from a good initial point. So the point is, if you start at an initial point that has low gradients, that you're basically, if the optimization landscape is quite flat, and then you set your initial point there, it's going to be a large problem because you can't find you're basically your gradients and your Hessians, all higher order derivatives, they are going to be flat. So you can't find anything out of that. So the important point is to start with a good initial point. So there are strategies in variational algorithms that do this, such as the parameters, initializing parameters such that the ensemble blocks evaluate to identity. So this is one idea. So basically what we can do here is to take tricks that variational algorithms have and apply it over to our post-variational strategy. Okay. So with variational algorithms, because you traverse through the landscape, even if your initial point is good, you can't ensure that your the updated gradients in later portions of the algorithm still work well. But with the post-variational algorithm, you always stay at the same point. You're just expanding outwards. So the initial point, having a good initial point ensures that your gradients still have a value to some extent, even with higher order gradients. Okay, so moving on to the second method. So the second strategy is what I call the observable construction strategy. So basically what we do is just to take a quantum, encoded quantum state, and then we do a lot of measurements. So these measurements could be based on polys for simplicity. Okay, so the idea is to build a arbitrary observable with linear combinations of polystrings. So again, the problem is if you take global polystrings, there's going to be a lot. There's actually 4 to the n power number of polystrings that you can construct with the basis to form a basis. So what we do is to again, we truncate at some level of to form just a local Hamiltonian instead of a global Hamiltonian. So even with this, the polystrings are exponential to k. So again, you have to truncate at some small order. Okay. So the number of measurements that you need for such a observable construction idea, if you do direct measurement on polystrings, you get a complexity to n to the k power on top of your exponential. You're basically exponential to k with based on the number of qubits n. So that's not really good. So there's this idea called the classical shadows, which I'm not going to delve into, but basically with this idea, which is to basically use global measurements to estimate local measurements, you can reduce the number of measurements, total number of measurements you need from exponential to n to exponential to z to 3. So it's still exponential to k, but the base is now 3 instead of 3n. All right, so does constructing a k-local Hamiltonian make sense in a way, in a sense, per se, because we're actually trying to estimate a possibly global Hamiltonian with a local one. So some theoretical work done by Robert Wang and Caltech with I think John Fresco, they have this theoretical guarantee with low degree approximations, which is for certain quantum states that are invariant under the single qubit gates, you have an observable, when you truncate your observable within power of k, which is log to the inverse of your error epsilon, you can actually estimate some arbitrary Hamiltonian within this approximation problem. Okay, so we haven't actually, for our work, we don't actually go into the theoretical aspects of this, but this does show that the observable construction strategy is actually might be possible under certain sets of quantum states. So heuristically, we can still use this as some approximation method. Okay, so the last one, which is the hybrid strategy, is a combination of both. As you can see from the previous ones, there are there are parts where you have to truncate directly. For the hybrid strategy, what we want to do is to try to deal with that kind of shortcoming. Okay, so for this part, you have both the ansatz and you have the multiple ansatz and you have the multiple measurements. You do both of them together. So this is basically just a hybrid strategy. So the idea is to construct both gradients and higher order derivatives with parameter rules, as with the ansatz expansion strategy, and to build an arbitrary observable using a linear combination of polystrings, as with the observable construction strategy. Okay. So why does this work? So we have two, we discussed the occurrence of gradient vanishment of gradients within this strategy. So we split into two parts that we want to discuss. The first part is when your observable is local, and the second part is when your observable is global. Okay. So with your local observable, and then suppose that when we construct our observable with local observables. Okay. So now when you expand your ansatz, you have the original ansatz that's fixed with the 0, and then you have your expanded gradient ansatz. Okay. So this is when you have the local. So when you have the global part, when you construct your observable with global polystrings, what will happen is that, okay, first off, when you take the gradient of ansatz in a global setting, when you have a global observable, this actually forms a barren plateau in variational algorithms. So basically what this does, this will actually evaluate to almost 0. So we can safely just truncate this part out. So the remaining part is where you have global observables that have the original ansatz. Okay. So this part would definitely not be the same circuits with your local observables because you have the same ansatz but different observables. But by taking the ansatz, the gradient ansatz of the local observables, what we can do is to hopefully approximate this area. Okay. So in a sense, we don't actually need global observables with the hybrid strategy. You only need local observables with some certain amount of gradient, some certain amount of ansatz expansion. Okay. All right. So with our strategies, what we want to do next is to build our post-variational algorithm, quantum neural network. Okay. So for each neural network, the basic building block it's a neuron. So what we do here is we set up a quantum neuron as follows. So we have a classical data, which we encode into a quantum state by some sort of encoding circuit. And then with this quantum data, we transform it by some unitary or ansatz into some quantum features, which can then be which we then observe against some observable. Okay. So the output of which, the expectation of the output would look something like this. So we have the data encoding unitary and the transformation unitary. Lastly, we have some observable. Okay, so when we have multiple of these quantum neurons and then we assemble them into a neural network, it looks something like this. Okay, so we have what we call the PQ hybrid strategy is inherited from our hybrid strategy, where we have P different ansatz and Q different observables. Okay. So this P different ansatz is generated from the ansatz expansion, and the Q observables is generated from the observable construction. Okay, so in total we have n different combinations, which is you get by multiplying them together. Okay, so basically our neural network system would look like this. You have a data point, you send it into different quantum neurons, which get an output. For the output, once you have the different output, you want to find the optimal combination of these quantum neurons, which then you add a set of trainable observables alpha. And then lastly, you take the sum of it to form some sort of estimation. And then where you train it is you take this estimation and then you find the loss between this estimation and the actual label. So this is how you train the neural network system. Okay, so the problem is, how do we find the optimal combination of alpha here? It's by convex optimization. Okay, so suppose So the idea is that we suppose we label each circuit from the P2 hybrid strategy from 1 to m. Okay? And then we're given a data set xi, yi with d data points and then we construct the two following matrices. Okay. So first we construct the data vector. So these are each individual point here is the data label. So from yi. Okay. And then so each of the elements from Q, okay, I think this is covering up. Okay. Okay. So the output for the ith column and the jth row, Qij, this stores the output of the ith quantum neuron with the jth data point. Okay. So basically here with our quantum neuron, we have the jth data point input and then the ith quantum neuron, which is from the PQ hybrid strategy. And then we take the output and we put it into the ij block of the matrix Q. Okay. So notice that each row would symbolize the features extracted from a single data point. So each row is each block for each row is basically the same piece of data put into different quantum neurons. So if we take the multiplication sum of this, the matrix multiplication of the first row and the vector alpha, what we get is the first block, which is the estimation, which then we can minimize against the actual data point. Okay, so this matrix stores all the outputs of the quantum neurons against all the jth data point. Okay, so we see here that this is actually just a linear system with Q as the features extracted from the data points, alpha as the optimization constants we want to find, and y as the actual labels. Okay, so we know that for linear systems, there's actually there's a provable output, closest output, which is the pseudo inverse of Q times y. Okay, so this is how we find alpha. Okay, so the next problem is because the outputs from these quantum neurons, as I mentioned, only the expectation value matches the transformation here. This is the expectation value. So each measurement from the quantum neuron, if we take multiple measurements, there's still going to be some error that's from the actual expected value that we have here. Okay, so the random measurements here born from the quantum neurons and set into Q, they will propagate all the way here to the difference. Okay, so in order to decrease this kind of measurement, this kind of error, we have to measure each quantum neuron, the output of each quantum neuron multiple times in order to minimize the error that's formed in Q and subsequently in the loss function that we have against the estimation and the actual label here. And so how many quantum measurements do we actually need to have, let's say, an epsilon error here? Okay, so we have the measure result Q prime and the expected value Q. Okay, so suppose that there's a difference between the loss here, that's epsilon. How much measurements do we need? Okay, so the answer is m to the third power times d. Okay, so this is basically the total number of measurements. So this is taken over all data points. So for each data point, what we need is the number of measurements is cubic to roughly cubic to the number of features that you have, the number of quantum neurons that you take. Okay. Okay, so I'm not going to delve into the calculations here because they're actually quite long and there's a lot of plain linear algebra. So I'm not going to delve into how this is derived, but the idea is it's cubic to the number of quantum features. Okay, great. All right, halfway done. Okay, so moving on to experimental results. So can we actually implement this post-variational quantum neural network in practice? So what we've done is we've taken a handwritten digit recognition dataset in computer science, and we encoded it into some quantum state using amplitude encoding and PCA. Sorry, excuse me. And then we run it through our neural network. So we find that when the observable is taken at 2 local, so we're taking we truncate at a low degree of 2, as well as the hybrid algorithm where we truncate at only 2 local observables as well as one gradient. So we only take the gradient for Ansatz expansion, and we only take 2 local. We actually reach an accuracy of 0. Basically, we reach an accuracy of 94%, which is quite close to the variational. We expect that if we take a higher order of observables as well as higher order gradient expansion, we might be able to get a better result. But for the experiments for this paper, we actually haven't done that yet. Okay, so what you see here is actually a low approximation, but there's actually quite good results.
Sorry, I have a question over here. Why, like, for the variational parts, there's no testing accuracy?
Yeah, we took it from the paper. So
yeah, so they didn't like put it testing accuracy. Okay.
Okay.
Which is this paper? Like, why is this paper? Do you know?
The variational paper.
Variational paper. Okay.
Yeah, okay.
I see.
They actually used it in training loss. So we took it from this paper that we took this data from was from another paper that was based on that Marischalt's quantum classifier.
Right. What ansatz do you use?
The ansatz was the exact same ansatz from Marischalt's paper.
Okay.
Yeah, I didn't add it here, but what we did was the gradient descent was to take that and then expand directly. Okay, so we use the same ansatz for expansion. Okay. Right. Okay. So moving on to the next part of my talk, which is based on problem-inspired post-variational strategies. Okay. So this is this wasn't included in like the introduction for this talk because I didn't tell Benny in time. Yeah. So this is a paper that we shot last month. It's on hybrid quantum classical and quantum inspired classical algorithms for solving that in the certain linear systems. Okay, so the note here is linear systems, so we know that there's already a problem or a Hamiltonian that we already fixed. Okay, so this could fall under the problem inspired spectrum of post-variational strategies. Okay, so unfortunately, due to time and the relevance, we are not going to talk about the quantum inspired part. Okay, so this is just mainly focusing on the quantum classical part. Okay, so quantum linear solvers, they're a large topic in quantum computing. So basically what we have is this is a linear system of a matrix AX equals B, and when we want to find X. Okay, so for fault-tolerant algorithms, there's the seminal matrix algorithm. For variational, we have also strategies such as the variational quantum linear solver. Okay, so what we want to talk about today is the combination of quantum states method, or the CQS method, by Robert Huang and Shore, as well as Patrick Ribbentrust. Okay, so this is where for this idea, what they do is they take the Hamiltonian, they decompose it into certain a set of unitaries, and then they use the unitary to grow a set of ansatz. Okay, so through this ansatz tree. Okay, so this is the general idea of their paper. For our paper, we do something that's very similar, but we actually don't use this ansatz tree. Okay, so what I'll talk about later. Okay. So for this paper, we focus on a specific type of linear system, which we call the banded circular linear system. Okay, so these are a linear system where the matrix A, or in our case, the matrix C, looks something like this. So you have the same value against the same diagonal on the diagonal. The next diagonal that circulates all over here, this part, this is all the same value. Okay, so you have C0 on the main diagonal, then you have C1 here, and then you have C2, so on and so forth. Okay, so these are called what we call circular matrices. Okay, so what we want to do is we emphasize banded here, which is apart from the diagonals that are k from the main diagonal, everything else is 0. Okay, so these are particularly restricted type of linear systems that we want to discuss. Okay, so why do we want to care about them? because they form the solution for one-dimensional elliptic PDE with periodic boundaries. So, for example, if you have a heat transfer problem, if you have a Poisson problem with a periodic boundary, you could solve it with the circular system. Okay. So how do we so as mentioned before, for these type of post-variational strategies, what we want to do is inspired post-variational strategies, we want to decompose the initial Hamiltonian. Okay, so because this is banded, we can basically just split each diagonal out and then take the number here and place it outwards. Okay, so you'll find that each diagonal that is from the main that is apart from the main diagonal, they could be expressed as the power of this particular matrix here. Okay, so this is what we call the permutation matrix. Okay. So if you notice, when we multiply it against some vector, it's basically just rotates the number of the vector around. Okay, so this is what we call a cyclic permutation operator. Okay, so a banded circular matrix can be expressed as a matrix polynomial. Sorry, excuse me. Matrix polynomial of the cyclic permutation operator. Okay, so another main property of these matrices is that they're actually diagonalizable by the Fourier transform, which is something that we'll use as part of the design of our algorithm. Okay, so for solving banded circular linear systems with the post-variational strategy, for linear, when we're given a linear system Cx plus b, when we solve for x, we find the pseudo inverse, or in this case, the pseudo inverse of c, and we times it against b. Okay, so how do we approximate the value of this? Okay, so given that our c can be decomposed into a matrix polynomial of q, the pseudo inverse of c can be approximated by some polynomial q with the degree of this much. Okay, so how do we looking at from it? How do we find it intuitive? How do we find this intuitive? So basically, you have a function f of q, and then basically when you take the inverse, you can just expand. When you take the inverse of a matrix, you can basically from viewing it from Taylor expansion standpoint, you can expand it into some matrix polynomial, right? And then so of c, and then once you plug c, which is a matrix polynomial q, into that matrix polynomial, you can get a matrix polynomial of q that symbolizes the inverse of the pseudo inverse of c. Okay, so if we truncate it at some certain degree, we should be able to approximate c, the pseudo inverse of c, by a matrix polynomial q. Okay. Okay, so the degree here, again, this is proven in our paper. I'm not going to go through the math today. So the idea here is to basically just decompose our C and then take higher. Basically, we take all possible powers of Q within this bound to construct our x prime, our explanation x. Okay, so again, we know that x is a combination of powers of q times b. So how do we find x? So basically, if there is, we can add like a coefficient, because x is a matrix polynomial of q. So basically, what we want to do is find the coefficients of that particular polynomial. So suppose that these polynomials are these coefficients are determined by we set these coefficients to alpha. Okay, so what we want to do is to find these alpha. Okay, so to solve this, to find alpha, we have to compute the overlap between c times qm b, which is basically cx, each individual part of cx, and then with the overlap of cx with b, and then the overlap of each individual component of cx. Okay, so once we have this, we can compute alpha. Okay, so how do we compute the overlap between these two parts? Okay, so this is a quantum subroutine called the Handwritten test, which could be used to measure this particular value right here. Okay, so we compute the different values of the inner product of qm b times b, which is basically you find, because c is also a polynomial of q, everything here, everything with the ansatz overlap can be written as some combination of b times qm times b. Okay, so what we want to do is to compute different values for b times qm, broad b times qm, q to the power times ket b, okay, for different m. Okay, so the next step is to implement this on a quantum computer. So how do we implement qm in particular as in a quantum computer? Okay. So remember that I mentioned that circular matrices can be diagonalized by a Fourier transform. So if you notice, Q is actually also a circular matrix. So this could also be diagonalized by a Fourier transformation. Okay, so we find that when we diagonalize Q with the Fourier transform, it actually forms a tensor product. So of rotation gates. Okay. So basically, the power of Q would also be can also be symbolized by the rotation of these rotation gates applied consecutively. And then when you have consecutive rotation gates, you form one rotation gate with a higher angle of rotation. Okay. So this Q can actually be formed by a QFT, a quantum Fourier transform, followed by this diagonalized matrix, which is a series of tensor products, and the inverse of QFT. Okay. So with the Hadamard test, what we actually do is this is the actual structure of the Hadamard test. Basically, what we need here is only the QFT. We don't need the inverse of QFT because we're measuring on the diagonalized matrix. Okay, so this Hadamard test, you can see that the depth of this circuit here is mainly just on the QFT side, because this diagonalizable matrix is just one layer of gates. So the main source of gates you have in this circuit comes from QFT, and then QFT, the depth of QFT is n squared, where n is the number of qubits. Okay, so we can find that implementing q to the mth power is actually independent to the power m. Okay, so this is the actual this is where our circuits. So for our system, our circuits don't actually increase in size. They're actually just relative to the number of qubits instead of the number of truncations that we need.
Sorry, I have a question over here. How about UV?
Okay, UV. Yeah. So in the paper, we do make an assumption that UV is easily implementable.
But B could be in general, right?
Yeah.
It could be very general, and then you have to find a unit tree to encode B. Right?
Yes, that's a problem of these algorithms.
So basically, you assume that you have access to the algorithm that easily prepared for you, and then you can apply this.
Yes.
Okay.
Yeah, because you need this as a quantum state.
So basically, it's just like once people get advanced in encoding the data in quantum states, then any improvement from there will definitely improve.
Yes, exactly. Right. Okay. So I'm moving on to the next slide. Okay, so as mentioned, we can collect all overlaps of CQM, CQB, and then as well as CQM with B. We collect them into two different matrices. So matrix B and matrix Q. And then so you see that when we multiply by alpha, it looks something like this. Okay, so this is our convex optimization problem. So once we have the values of B and Q, we can actually just find the values of alpha by classical computation. Okay, so the last thing is for our method, how many quantum measurements that we need. So basically, how many quantum measurements do we need to calculate all the overlap such that the convex optimization still works? So to find our x that is in this form, we need, as mentioned, our truncation t should fall within this bound of k times kappa log kappa divided by epsilon.
Actually, what is kappa though?
Oh, kappa is the condition number of C. So there's also the assumption that C is well conditioned. Okay. So this also falls into the other quantum algorithms such as HHL. Yeah. But in this case, the kappa scales linearly, so it's not as bad as, let's say, like the CQS case where you have exponential. Okay. So suppose that when we plug this answer to our linear system Cx minus b, which we take the two normal, we want an approximation that is close to the minimal answer plus some additive error epsilon. Okay, so this is the task we want to achieve. So how many measurements do we need to find an x that is close enough? Okay, so when we talk about epsilon, this is inclusive of the polynomial approximation error here, where we truncate the degrees of x, as well as the random measurement error that's formed from the errors of quantum measurement. So the number of quantum measurements that we need is square root to k, which is the width of the band, and then 4 times the kappa, which is the condition number, and inverse to 5 times of the epsilon. Fifth power of the epsilon, which is the error here. Okay. It's not too bad, but I do believe this is something that we can work on.
But what is the bigger norm of the collision CL?
CL?
Yeah, because like over here it depends on B, right?
Yes,
so
yes.
what is the like for typical problem, like what would be the value of CL? Would it be too big or?
So this is basically based on the problem. So the problem
Yeah.
you're trying to solve. So if you have like this second matrix, let's say for Poisson equation, this is
Okay.
4.
Uh-huh.
Yeah. So for heat transfer, it's also somewhere between like 4 to, it could be large. But generally for, let's say for tridiagonal cases, or for physical cases, this wouldn't be that large.
Okay.
So, and this is based on the problem itself. So
Mhm.
this comes with the problem,
Mhm.
the problem matrix itself. So
Yeah. So
yeah.
if as long as like for typical
Yeah.
problem of interest,
Yes.
this value will be small and then
Yes. Okay. Yeah. So we also did some numerical experiments for this setting. So we ran our hybrid algorithm on Qiskit AR simulator. We find that it's actually quite close to the matrix of multiplication. This is on logarithmic scale. So the error seems a bit large, but it's actually not, because the y-axis is on the logarithmic scale. Yeah. So we actually ran it on like a IBM hardware, and we find that the error is actually quite acceptable in a sense. Yeah. Okay.
how many qubits?
So this is 5 qubits.
Okay.
And this is 3 qubits.
Okay.
Yeah, the quantum hardware is 3 qubits because we do need QFT, which is hard to.
Right.
Yeah.
Okay.
So that's the problem of that of the algorithm. Okay. Yeah. So to conclude my talk, well, post-variational strategies for quantum machine learning. These are methods that use quantum computers to compute measurements of operations on several fixed ensembles, which, in contrast to variational, is a tunable parameterized ensembles. We take the optimal combination of which can be found by classic convex optimization. So instead of optimizing over the quantum landscape, we optimize over classical optimization. Okay. While heuristical applications of such strategies can be useful, I believe that one important direction for future work is finding the restriction and special cases for both problem agnostic and problem inspired approaches where a polynomial converges guarantee, such as the circular linear system case. Right. So that concludes my talk.
Yeah. So thank George for the very interesting talk, and yeah, for the audience, if you have a question, just like unmute yourself or type of questions. Yeah, Can you have questions, right? So maybe you just unmute yourself and ask the question.
Hello, can you hear me?
Yep.
Hi, so can I ask about the convex optimization part again? Because it is not clear to me how the vector alpha are points on the convex set. So maybe can you explain that part? I might have missed it.
Basically we just run it against some convex. Okay, so in the actual paper, what we do is we split the real part and the imaginary part of V and Q, so that everything in alpha is a real number. Okay, so and then this is basically everything here. It can be solved by classical convex optimization problem. Convex optimization packages you find online. Yeah, so this is actually everything here. It looks a bit quadratic, right? So it's basically just some classical algorithm that we run. Does that answer your question?
So the objective function is convex, but are the vectors, so the points alpha or the vector alpha, are they elements on the convex set, elements of the convex set? Because the state has to be normalized, right? So how do you account for that?
The state has to be normalized. Okay, so
Like-
yeah, I did miss that. The assumption for this is that B is already normalized. Or is that not what you're asking? Sorry,
Like, because if the states have to be normalized, then that is a constraint on the vector alpha. Then with the constraint, I'm not sure if the vectors alpha form the convex set, are points of the convex set.
well, alpha is not normalized. We don't normalize alpha in this part. There's no constraint on alpha because while B is normalized, we don't set any restrictions on X.
Right, as in, but the coefficients alpha have to be such that the linear combination is a normalized field, right? So that is a constraint on alpha.
Because we do an approximation, so the result X that we get is an approximation, and then C itself is not necessarily a normalized matrix.
Okay, thank you.
Yeah.
Okay, so we have two more people asking the questions. Maybe Rahul, you can go first, and then Dario will go after.
Hi, sorry. Can you go back to the first part of the talk?
Yeah.
To the like when you showed the results for the MNIST, like the digits. Yeah. So this accuracy that you get, is it for multi-class classification or like binary classification?
This is for binary.
Okay.
We only take 0 and 1, but we do include the multi-class in the paper.
Okay, and like I'm just wondering what kind of results you guys get like for the multi-class.
If I recall correctly, I think 84%.
80%. Okay, well, okay.
How big a data size you use?
Yeah, thanks a lot. Yeah.
I think it's the full data. For multi-class, I think it's the full data. I kind of forgot.
Okay.
The details are in the paper.
Okay.
Binary, it's a smaller set.
Okay.
Yeah. And Dario, maybe you can unmute yourself to ask a question.
Hi. Yeah, just a naive question. In the beginning, it seems to me that it has quite some resemblance, although much better organized in a certain way, structure, to reservoir computing. I would like to hear what you think about this.
Actually, I haven't considered the similarities of that. Sorry.
Okay.
Okay. Yeah, it's a good question. I'll check on that later.
Okay. Thanks.
Do we have any question? Yeah.
In the second part, you talked about barren circuits.
Yes.
So the example you gave was one-dimensional.
Heat transfer.
One-dimensional system.
One-dimensional electric PDEs.
So there's also high-dimensional PDEs.
For high-dimensional, you have in some cases you have block, right? Yeah. So that's actually something that we're trying to work on right now. Yeah. So it's not really covered in this paper yet. So it's something that we're trying to work on for future work. Yeah.
You mentioned that you actually have a second part of the work in the same papers, right? Like the problem is barren.
Problems, right? Yeah.
Yeah. So could you briefly explain a bit of how would that be?
Okay. So basically, it follows Ewing-Tang's idea of sampling from vectors, vector sampling to replace the quantum state. And so basically the implementation of Q in classical computing, I mentioned this is just permutation, right? So once you have a sample and query access to the vector B, you can find Q times Q to the nth power times B quite easily by shifting the indexes. Yeah, so that's basically the idea. Yeah, so in the quantum inspired algorithm, we don't actually use Fourier transform, but it's just here for implementation for the quantum computer. Yeah.
So how is the performance compared to the typical one?
Yeah, so it's somewhere between the hybrid algorithm and random bias.
Oh, okay.
But yeah, given that we have sample access for B, which I would say it might be a stronger assumption than having a well-prepared quantum state, having a quantum state for B,
Right.
due to the hardness
Okay.
assumptions, which we do also talk about in the paper.
Right. So do we have any questions from the audience? Yeah.
So all this is based off polynomial expansion.
Yes.
Cost function. So you then assume that the cost function has some non-zero radius of convergence for the expansion.
Yes.
So I wonder whether this is you're imposing some bias on the form of the function itself, and this limit the expressive power of this approach.
Yes. So for the inspired part, we can find like a bound for the expressibility such that your epsilon includes both the approximation error and the measurement error. This is not exactly the case for the problem agnostic approach because we don't know how well the neural network actually approximates the true answer. So that's the part where more work can be done on problem agnostic part. But for, as I mentioned, for certain quantum states that are formed by distribution over some quantum single duplicate, there's also an existing theory of recurrency for the approximation error as well as the measurement error. So you have an approximation error, you have a truncation bound that relates to the approximation error. Yeah. So of course this could be expanded. Yeah, it's just it's not something that we actually cover in this paper. Yeah.
Okay, cool. So if there's no more question, then we can thank our speaker again. Thank George for the very interesting talk, and hopefully there will
Thank you
be
for having me.
more work in these post-variational methods to expand our tool a bit. Yeah. So thanks everyone again for attending the talk, and see you again next time. Yeah. Ciao.